Hello everyone and welcome to the practice video for linear speed and angular speed. Before we proceed, I would like to say something. Yesterday, I uploaded a video that is the test video for the angles and angle measures. I suggest you should not watch that. Watch these practice videos first, okay? Do not watch that for a moment. Watch these practice videos first. The practice videos for linear speed and angular speed. So why do we need to watch these practice videos before we watch the test video? The test video is the overall practice for that topic. Okay? Like in angles and angle measures, it consists of three subtopics, right? The degrees and gradients, the length of the circular arc, and the linear speed and angular speed. So before we proceed to the overall test or rather overall practice for that topic, we must have practice videos for each of the subtopics. Okay? So degrees and gradients has its own practice videos. Length of the circular arc has its own practice videos. But for this case, linear speed and angular speed does not have practice videos. Therefore, we are going to have practice videos first before we proceed to the overall test. Okay? Because that test is basically the coverage of all the subtopics we've learned in the angles and angle measures. Okay? So now you understand. I think now you understand my point. Okay? Have these videos first, then we can now proceed to the test video. Okay? So let's now proceed. True or false? The applications of arc length and angle measure are linear speed and angular speed. The applications of arc length and angle measure are linear speed and angular speed. The answer is true. Okay? It is true. Right? So, you see, let's just say I have a circle here. Okay? Then we have a two radii, and between radii, we have an angle here. Okay? So, you see, we know before that we can get the arc length, which is this one, that is intercepted by the central angle by using this formula, right? S is equal to r times theta, right? Now, we can apply that in real life, okay? Suppose that this circle is a circular path, okay? Because it's possible that you can walk, jog, or move an object in a circular path, all right? So let's just say that you are walking around a circular park, all right? You start from here at this point and you end at this point, okay? So what would be the total distance? So the total distance traveled would be your arc length. And as you can see, we have an angle given here. So that is already a self-explanatory for the application of angle measure, right? And of course, yeah, I forgot to mention, finding the distance between the 2 points in a circular motion is the application of arc length. Now, you see, uh, when it comes also to distance, there's also a speed, okay? And you see, linear speed and angular speed are the applications of arc length and angle measures because these two will find the speed of an object in a circular motion. Okay? So please do not ask me what will be the formula because I call this one, it would be easy for you to answer the other statements because there are other statements out there will tell you whether the formula of this linear speed is this or not. Okay? So at least now I tell you that these two are the applications of arc length and angle measures. Okay? So let's now proceed. Okay? I already told you once again that in every distance, there is always a speed. Okay? And remember that the speed is v is equal to d all over t. right? So that's the formula of the speed. But how about for the linear speed and angular speed? We will find it out. Now, the formula of linear speed is W is equal to theta all over T. So what do you think is the answer here? Well, the answer here is false. Okay, false. See, this is why I never mention the formula of the linear speed and the angular speed. Okay, because you will know exactly what will be the formula of the linear speed. So yeah, the answer is false. This one is actually for the angular speed, not the linear speed. Because for the linear speed, you're not going to use this. Rather, you're going to use V is equal to S all over T, where once again, your S is your arc length. Okay? So, yeah, it's false. Next. To find the angular speed, just divide the central angle by the time. To find the angular speed, just divide the central angle by the time. The answer for that is true. Okay? I think this is a general statement, not a specific statement. Okay? Yeah, generally speaking, yeah, just divide the central angle by the time. Yeah, true. But if you're asking me specifically, it depends. Because if the angle here, for example, is in degrees, like this, then no. Okay, you can. What you're going to do is you're going to convert it into radians. Okay? So, yeah, to be specific, you need to convert an angle that is in degrees into radians so that you can divide it by the time. Right? So, let's now proceed. The main reason why the direction of the linear speed is linear is because of its perpendicularity to the radius of the center. Again, the main reason why the direction of the linear speed is linear is because of its perpendicularity to the radius of the center. The answer is true. Okay, true. So let me give you let's just say visualization. Okay, so let's just say let's just say an object, much better. An object rotates in a counterclockwise. You get me? So now let's just say you start from this. Okay, let's start from this since we have this thick point here. Then let's just say you end here. You end it here. Okay? So this is these are the radii or in singular radius. So if it rotates in counterclockwise, okay, then you will expect that this object will move at this direction, right? But the path, yeah, it's in circular, just like from here going there. Yes, yes. But the direction of it is perpendicular to the radius. So it could be from here or from there. But since it rotates on a counterclockwise, so it will rotate here. So let's just say we are at its final position, which is here, right? Here. So here, again, since it rotates on a counterclockwise direction and it is perpendicular to the radius of the center, it will look like this. Okay? Now, what if, let's just say, the object is here? So what will happen? What will happen is that the direction, the speed will go there. Okay? So yeah, the answer for that is true. Why? So next. Linear speed and angular speed are related to each other. Linear speed and angular speed are related to each other. The answer is yes. They are in fact true. If we're going to draw a graphical representation, like for example, we notice that the object moves in a circular path, and this is the initial, and that's the starting point. So here, uh, there's always an angle in between. Okay? So let's just say you want to find the speed of the object coming from here up to there, right? So you need is the distance, then the time duration for the object moves from this point, which is the initial, and up to this point, which is the final. Okay? So yes, we can use this formula to find the what? The the speed of the object moves in a circular path. Okay? But at the same time, you see, there's an angle formed here. And uh, imagine that the angle here starts from this and it forms by rotating it at this direction. What happens to the angle? It increases, right? Like imagine, it's like this, then later it become like this, then later it become, sorry. Then later, once you rotate it even more, it becomes like this, right? And of course, it become like this. Okay? So you see, even angles need speed. So here, the angle here, okay, to find the speed of the angle formation is you will use this one, right? Theta all over t, which is this one, okay? Plus, you can actually use the angular speed to find the what? To find the linear speed, okay? So I won't tell you what would be that formula, but yeah, I already told you the clue that linear speed and angular speed are related to each other. In fact, they have their own formula that consists of linear speed and angular speed. Okay, so let's now proceed. Okay, next. Okay, whoa. Let's answer this one by one. Okay, linear speed is inversely proportional to the angular speed. Linear speed is inversely proportional to the angular speed. The answer is false. Okay, this is false. Why? Why is it false? When we say inversely proportional, you're implying that if linear speed increases or it goes faster, then the angular speed decreases or it goes slower. Which is wrong, by the way. Because if you're going to look at my graphical representation last time, you know, once the angular speed increases, what happens to the angle? It also increases, right? It's like you have these two sides, okay? Let's just say this is the object, and let's just say you rotate this side. What happens? Not only that, the ball here, it rotates from here up to there, but the angle here, it also forms into a bigger angle, right? So wrong, okay? Rather, it is what? Directly proportional, okay? Not inversely, because inversely, you're implying that if the linear speed increases, the angular speed decreases, which is wrong, okay? Rather, it is directly proportional, meaning if the linear speed increases, the angular speed increases. If the angular speed increases, the linear speed increases, and vice versa, okay? So it's directly proportional. Now, last but not the least, when you want to find the linear speed, but the given involves the radius and the angular speed, you will use v is equal to r times theta. Again, when you want to find the linear speed, but the given involves the radius and the angular speed, you will use v is equal to r times theta. The answer for this one is true. Maybe I think I mentioned the clue earlier, right? Right? I told you that linear speed and angular speed are related to each other and they have their own formula. And which is this one, which is correct. Okay? All you need is the radius and angular speed for you to find the linear speed. Okay? So yeah. And that's it, guys. We're done with the true or false. Now to the next video, expect that we're going to solve some problems. See you soon.